Okay, what I want to talk about, I'll begin by talking on the usual story that we hear about the fact that CO2 is allegedly the culprit behind the global warming that we have seen. I'm going to spend a little bit more time than usual about doing this because I don't think we've seen in the past day and a half a good exposition why the standard picture is not working very well. So I want to dwell on it a little bit. And then once I demonstrate that the story that we hear from the IPCC is faulty in many respects, I want to introduce another explanation for at least part of the warming. And then I want to show you all the evidence. And once you do introduce that, and that is that the sun has a large effect on climate, you realize that you get a much more consistent story explaining for what happened over the 20th century. And besides, it will help us understand what will happen in the 21st century and also what happened on other timescales as well. Okay, so the standard picture about global warming is the one we hear from these guys. And the standard picture is this. We have seen that there is global warming. We can see it here. This is temperature measured with different stations over the past 100 years. In black, we see that the temperature has increased. It could have some contamination, but basically the temperature has increased. Now, what you can do is you can take global circulation models, which are computer models which allegedly include all the relevant physics. You can then plug it put it into the computer and then start cranking the computer and then see what you get. So you take different sources for changes in the energy budget for the radiative forcing, and then you simulate what happens to the climate. And what you see here in red and in the mustard-colored graphs are different realizations that you find when you integrate with those kind of computer models. And what the IPCC tells us basically is that, look, this is what we know about the radiative forcing. Most of the forcing is governed by greenhouse gases. We plug it into the computer, and lo and behold, what do we get? We get that the temperature should increase, and it agrees with what we actually see. Case closed, CO2 is guilty, and then we have to move forward. But this story is much more complicated. Okay, so first of all, what is the first problem? The first problem is that the warming that was predicted by the IPCC is not seen. If you look at the different IPCC reports that we have had, you'll see that in all reports, the climate sensitivity is basically the same. Namely, if you double the amount of CO2, the temperature should increase somewhere between 1.5 and 4.5 degrees. In the last report, it actually decreased a little bit, the range from 2 to 4.5. But what it tells us is that because this value didn't significantly change, it means that the predictions which were made in the first IPCC report in 1990 should still be valid, okay? But what we see in essence is that the global temperature increase is now roughly at the lower end of the estimate, if not even below the low estimate. So basically, the predictions which were done by the IPCC are wrong. Now, in any decent scientific theory, when you see that the predictions don't fit that the realizations don't fit the predictions, then you go back to the drawing board and you see how you can change or modify the theory in order to explain it. But no, in the IPCC process, what you do is that every 6 years you come out with a new report and then you reset your prediction clock. So you're always, by definition, inside your range of predictions. Okay. Another problem is that the models predict one warming, but you don't really see it in reality. What you see here is that the models predict that the temperature distribution of the warming should be such that most of the warming is around 10 kilometers. It also tells us that the warming should be over the subtropics more than the tropics. But what you see in reality is that the warming from Radisson data is, I don't have a reference for it. The warming over the, with the Radisson data, the warming at higher latitudes is lower than what the models predict. So if you think that CO2 had some kind of a fingerprint with which you can detect different kind of warmings, then what you see in reality doesn't fit the model predictions. So there's probably something wrong with the model. Okay. Another problem is that the models, the climate models which are used to predict the temperature warming are oversensitive. And you can see that here. This is a graph from the previous IPCC, the third IPCC report. What you see here are the temperature, the measured temperatures, or the reconstructed temperature, to be more precise. And in gray, you see the range of models which model the temperature increase over the 20th century. Now, what you see is that whenever we have had a large volcanic eruption, the temperature on Earth decreased by quite a lot. Like when Krakatoa exploded, when volcanoes explode, and they are stratospheric piercing volcanoes, namely they put dust into the stratosphere, the dust which sits in the stratosphere can block sunlight, and it can do that for 1 or 2 years before the dust settles down. You expect this dust to reflect some of the sunlight and therefore cool the Earth. And you know there are measurements which tell you how that changes the radiative forcing. You can plug that into global circulation models and see by how much the temperature should have decreased. And in fact, when you look at the global circulation models, you see that when you had large volcanic eruptions, the model give you that the temperature should have decreased by quite a lot. In fact, the models give you that such large volcanoes should decrease the temperature between 0.3 and 0.5 degrees. In reality, whenever we had large volcanic eruptions, the average temperature decrease, this is the temperature before and after the 6 strongest volcanic eruptions since Krakatoa, you see that the temperature decrease has been, on average, 0.1 degree. Why is that? That's so because the global circulation models are too sensitive. They're more sensitive than reality. Okay. Now, if we're talking about sensitivity, let's try to understand where the source of the problem resides. We know that when we heat the Earth, because, for example, we double the amount of CO2, we change the energy budget. If Earth didn't change anything except increase the amount of CO2, what we would expect is to see a temperature increase of 1.2 degrees Celsius. Now, in reality, Earth changes as well. If you heat the planet, then you also heat the oceans. You get more evaporation. Water vapor is a good greenhouse gas, so you get a positive feedback which increases the temperature even more. But if we have more water vapor in the atmosphere, we also form more clouds. And it turns out that clouds are the dominant uncertainty in global circulation models. One model can give you has one recipe for the clouds, and it will tell you that the clouds will change by a little bit. Another model will tell you that the clouds will change by a lot. And this gives a change in sensitivity. I mean, you can play with this recipe for cloud cover and get sensitivities between, say, 1.5 or 1 degree increase to 5 degree increase for doubling the amount of CO2 just by playing this with this recipe. And this you can see with this graph. This is a paper, this is a result which was published already in 1989. What you see here, this is the sensitivity of the climate models. And this is a range of climate models that were in existence back then. And here what you have is the inherent sensitivity or feedback that the model has through cloud cover. Because you see that all the models sit on very close to a straight line, it tells you that this thing, this parameter, this sensitivity or this feedback through cloud cover is the dominant source of uncertainty in climate models. Okay, so the reason the IPCC cannot predict the temperature increase is that because nobody knows what is the correct recipe to use in order to describe by how much the cloud cover is going to change if you heat the planet by a given amount or you change the amount of water vapor. Another problem is that there's no fingerprint which proves that CO2 is the thing which does the warming. Now, someone would say, just a second, we saw Al Gore's science fiction movie. And in that movie, we have seen Al Gore show us this graph where you have a CO2 reconstruction and temperature reconstruction from ice cores, which were drilled in Antarctica in this case. And he tells us with his authoritative voice, the relation is complicated, but we see that when there is more CO2 in the atmosphere, the temperature is higher. Why? Because he wants us to believe that CO2 causes a large temperature increase. What he doesn't tell us is that when we have ice cores with a good enough resolution, which is usually ice cores coming from Greenland and not from Antarctica, you see that always you have a lag such that CO2 lags behind the temperature and not vice versa. Okay, so how can the CO2 affect the temperature before it itself is affected? I mean, we know that CO2 must have some effect on the climate, but this correlation that Al Gore has shown us doesn't prove anything or doesn't quantify anything in this direction. Now, the reason we see this effect is the same thing you have in this thing. You have a Coke bottle, and if I forget this Coke bottle in a car in a hot summer day, probably most people here don't know it because there are not a lot of hot summer days here. But if I forget it in Israel and I open the Coke bottle, what will happen is that everything will fly out. And the reason is that what we have here is CO2 which is in the air and CO2 which is dissolved in the Coke. And we have much more CO2 which is dissolved in the Coke. And this CO2 is in some balance between CO2 which is dissolved and CO2 in the air. Now, this equilibrium depends on the temperature. Now, in the oceans, it's more complicated because there are a lot of chemical reactions, and it's not just simple dissolution in the ocean. But still, in Earth, we have that there is 70 times more CO2 in the ocean than there is in the atmosphere. And the equilibrium between CO2 in the atmosphere and CO2 in the ocean is temperature dependent, such that when we heat the oceans, CO2 is released, and it takes several hundred years for the oceans to mix, and that's the origin of the lag. Okay, so Al Gore has shown us the Coke bottle effect. Okay. In fact, on longer timescales, there are much larger variations in the CO2 which have nothing to do with this temperature-dependent equilibrium. On longer timescales, we have CO2 variations which are due to geological activity. We have more volcanic activity or less. And then what we see is that over a time span of hundreds of millions of years, we had variations in the atmospheric CO2, which can be as much as a factor of 10. And we see that there are no correlations, or there's no correlation between the CO2 in the atmosphere and the temperature on Earth, which here you see reconstructed using oxygen isotope ratios in fossils. Okay, does anyone here see a correlation? No, I didn't think so. I didn't either. Okay, this can be used to place an upper limit on the effects of CO2 on the climate. One which is just below the range of the IPCC. Okay, another problem is that global warming is not unique. I mean, we heard time and again the temperature increase over the 20th century is unique, and therefore it's not natural, and therefore it must be human. But in reality, it's not unique. Temperature over the 20th century, or say the latter part of the 20th century, is similar to what we had, say, 1,000 years ago, or less than what we had in the Holocene maximum 5,000 years ago. In fact, if you open the first IPCC report, you see that there were temperature variations which were quite large. But it's like George Orwell's 1984. We woke up one day and suddenly there was no medieval warm period, there was no little ice age, there was just the hockey stick. Now, anyone who has been alive during the past year or two has heard of climate gates, and know that the hockey stick is the hockey stitch. Okay, next, another problem is that we are told that the global circulation models nicely explain the 20th century, and therefore they must be correct. But in fact, if you open the draft of the first assessment report, you'll find this graph. What you see here is the probability distribution function that humans are responsible for different radiative forcing. And the reason that there is a large error in it, and in fact we humans could have been responsible for some warming, is because of the indirect aerosol effect. We could be affecting the clouds in such a way that we could be cooling the planet, which is what we thought we were doing in the 70s. This means that we could have explained almost any temperature increase, or in fact a decrease, over the 20th century. So the fact that they can explain it doesn't mean a lot. Okay. Another line of evidence that the IPCC, or people advocating the IPCC, use in order to explain why humans are responsible is because they have nothing else to explain with the temperature change over the 20th century. But there is something else which has changed significantly over the 20th century. And in fact, I'll show you now all the evidence to support that it does have a large effect on climate. And the thing I'm talking about is the sun. Over the 20th century, the solar activity has increased, and this has had a warming effect, which explains a significant part of the warming. The sun is an active star. It changes its activity. It has the 11-year solar cycle, and it also has secular variations on longer time scales. This is probably one of the nicest graphs demonstrating that the sun has a large effect on climate, or has a clear effect on climate. You see here a reconstruction of the temperature over the past, a reconstruction of solar activity over the past several thousand years. This is by the Mangini group in Heidelberg. And what you see is carbon-14, which is formed by cosmic ray spallation on the top of the atmosphere. And this is a proxy of solar activity, as we'll see in a few minutes. And this is reconstructed from tree rings. What you see in the bottom part of the graph is a temperature reconstruction, which is a proxy of the temperature in the Indian Ocean. Basically, oxygen 18 is heavier than oxygen 16. So water with oxygen 18 is heavier than water with oxygen 16. So the evaporation rate from the oceans is different for the two types of oxygen, but it's temperature dependent. So because of this bias, the oxygen that falls and in Oman in this case, and then forms these stalagmites in caves in Oman, this oxygen mirrors the temperature of the Indian Ocean. And clearly you see a very nice correlation between the solar activity on one hand and the climate in the Indian Ocean. This is another example. Here you have, again, the carbon-14, which is a proxy in blue, the carbon-14, which is a proxy of solar activity. And in black, you have a sedimentation record from the ocean seafloor in the northern Atlantic. So this is a proxy of the climate in the northern Atlantic. Basically, what happens is that when you have colder winters, ice can reach further latitudes which are further south and melt and deposit its ice rafted debris further south. And this you can see from the seabed cores. And again, you see a correlation between a climate proxy, this time in the northern Atlantic, and climate on Earth. And the solar activity. Okay, now where does this link come from? You could say, okay, we know that the sun changes its solar irradiance, that just the total output might be doing it, but it turns out that it is not possible to do it with the solar irradiance because the sun changes its luminosity, its irradiance only by 0.1%. And that's not enough to explain this or other results that we have seen. What? Sorry. You must have some kind of an amplification mechanism. And it turns out that the mechanism which has the most amount of evidence to support it, which can explain both the size and other things, is the cosmic ray climate link. And what is this link? So I'll explain what is this link, and then I'll try to briefly review the evidence. And then we'll try to understand what does it mean for the 20th century temperature increase. Okay, so over the solar cycle, we know that the sun changes its activity. Now, with this change in solar activity, we have a change in the solar wind. The solar wind is a very tenuous wind, but driven off the sun. But what it does, it modulates the flux of high energy particles which come from outside the solar system, which are called cosmic rays. These particles are actually formed in supernova explosions. Now, the interesting thing is that these cosmic rays, these high energy cosmic rays, are energetic enough to actually penetrate the atmosphere, and they dominate the amount of ionization we have in the bottom part of the atmosphere. Here inside the room, we may have ions from concrete. Okay, so maybe here inside the room, they don't dominate the ionization. But if you go out, the amount of ions in the atmosphere depends on the flux of these high energy particles which comes from outside the solar system. Now, the high energy particles from the sun are not energetic enough to penetrate the atmosphere, and therefore, it's a more active sun doesn't increase the amount of ions. It's exactly the opposite. A more active sun increases the solar wind, which blocks the flux of cosmic rays, and therefore reduces the amount of atmospheric ionization. Now, it was suggested already in 1959 by Edward Ney that if there would be some kind of climatic variable which is sensitive to the amount of atmospheric ionization, you will immediately get a link between solar activity and climate. And in the 70s, it was suggested that the number of cloud condensation nuclei, or the formation of condensation nuclei, could depend on the flux of cosmic rays, or sorry, the number of ions you have in the atmosphere. And in the 90s, there was observational evidence which has demonstrated that the cloud cover indeed follows the flux of cosmic rays reaching the Earth. Okay, so the link is such that when the sun is more active, you have a stronger solar wind, you get less cosmic rays, less atmospheric ionization, and therefore less formation of cloud condensation nuclei, and you get clouds which are less white. And that's because clouds with less condensation nuclei have a lower surface to volume ratio. And if you have clouds which are less white, you will reflect less of the sunlight, which means that you get more of the sunlight, which means that it's going to be warmer. Now, it's a very long link, but there's evidence now for every part of it. Okay, as you can see here, this is the flux of cosmic rays reaching the Earth, and this is the amount of low-altitude cloud cover. Notice that both graphs look exactly the same, so it doesn't matter which one is which, right? Let's see. Cosmic rays are in red. Another way of seeing how cosmic rays affect the climate, and that's actually the way I entered this field, is to look at variations in the cosmic ray flux which have nothing to do with solar activity. And it turns out that over geological timescales, the flux of cosmic rays reaching the Earth can change by a factor of a few between different, when we are roaming the galaxy, sometimes our environment has more stars exploding in supernova, and sometimes less stars exploding in supernova, and therefore we sometimes get more cosmic rays and sometimes less. And what you can see here in this graph is the reconstruction of the cosmic ray flux based on iron meteorites. That's on one hand. On the other hand, you can see here the reconstruction of the temperature using fossils, using oxygen 18 to oxygen 16 isotope ratios in these fossils. And clearly you can see that there is a correlation. There was no correlation with the CO2, but there's a large correlation, a huge correlation with the flux of cosmic rays reaching the Earth. Okay, another more evidence. Here, what you see is decreases, which are several days long, which are called Forbush decreases. And these are, what happens is that when you have a gust in the solar wind, several days later, this gust reduces the flux of cosmic rays reaching the Earth. So you get a reduction here in red of the cosmic rays reaching the Earth. And here, as a consequence, you can see that the number of aerosols that you have over the oceans and 3 different independent cloud data sets all show you that as a response of these Forbush decreases, you get a change or a reduction in the cloud cover on Earth. This is a lab experiment which was run in Copenhagen. This is Henrik Svensmark here. And what you see in this graph is that when you increase the amount of ionization in the chamber, you increase the formation rate of condensation nuclei. This experiment was repeated in CERN with a better control of what you have, of the conditions that you have in the chamber. And you can see again exactly the same results. When you increase the amount of ion concentration in the chamber, you increase the nucleation rate inside the chamber. So we see that if we play with the density of ions, we'll play with the density of condensation nuclei. What does it mean? Here, it means that we're going to change the properties of cloud cover, and you can see that with this example. If you Google ship tracks, you'll find this kind of pictures. What you see here is these are not contrails of planes. Basically, what happens is that as ships burn the dirtiest fuel possible, it's international water, so obviously they burn the cheapest fuel, which is dirty. The dirty fuel releases a lot of exhaust particles, and these exhaust particles serve as cloud condensation nuclei. So you see that if you increase the number of cloud condensation nuclei, you get clouds which are much whiter. Okay, so the same thing happens with the cosmic rays increasing the condensation nuclei in the atmosphere. Okay, so we've seen that there is a large link. The sun affects the climate. And now there comes the question, how large is this link? And can it be important for the climate change over the 20th century? And the answer is that, well, if you look at the changes in the solar irradiance, you get variations which are about 0.17 watts per square meter. For comparison, we get on average 240. But if you look at the change in the cloud cover over the 11-year solar cycle, and you use satellite measurements to translate this change in cloud cover into a change in the energy budget, you'll see that the cloud cover change corresponds to about 1 watt per square meter. So obviously the change in the cloud cover, because of cosmic ray flux variations, is much larger than the change in the solar radiance, so it's a much larger effect. You can actually quantify it in another way, and that is to look at the amount of heat that the oceans have absorbed every 11 years in sync with the 11-year solar cycle. Perhaps the best data set is this one. What you see here is the rate of change of the sea level in millimeters per year based on tide gauges. And this you can see here in black. And in red, you can see the solar activity, and in particular, you can see the 11-year solar cycle. So what you see here is that every time the sun is more active, the oceans heat and expand thermally. And this thermal expansion of the oceans can be used to quantify the effect that the sun has on the climate. Okay? And lo and behold, what do you get from it? You get that the heat which goes into the oceans every solar cycle is exactly 1 watt per square meter, which is consistent with what you get from the clouds. Okay, so you can use several data sets like the tide gauges or the sea surface temperature or the ocean heat content with buoy data. And you can estimate the change in the radiative forcing due to the cloud cover changes over the 11-year solar cycle. And in all cases, you get something which is roughly a little bit more than 1 watt per square meter. For comparison, this is the radiative forcing related to the total solar irradiance. So when someone from the IPCC tells you, oh yeah, sure, we do take the solar activity into account, they'll actually mean that they take this thing into account. They don't take the real effect that the sun has on climate. Okay, Why is that important for the 20th century? It's important for the 20th century because if we look at solar activity over the 20th century, solar activity has increased. What it means is that an increased solar activity should correspond to some positive radiative forcing. As we said, stronger solar activity means less cosmic rays, less ionization, less cloud cover, higher temperature. Okay, so in order to quantify and understand the 20th century better, a student of mine and I built a climate model which includes diffusion into the oceans and coupling between the land and oceans, and a lot of free parameters like the climate sensitivity or the actual forcing that the indirect forcing that the sun has on climate, or the diffusion constant into the oceans. And we said we're ignorant, we don't know those numbers. Let's see if you can find climate variables for which you can explain the 20th century temperature increase. And once you do that and you optimize over the parameters that you have and make sure that they are consistent with the observations, basically when we allow the sun to have a large effect on climate, we can explain the temperature increase over the 20th century with a residual which is twice smaller than what the global circulation models do without the sun. Okay? So the sun helps us understand temperature change over the 20th century. You can use the same model or the same range of model parameters which fit the 20th century to integrate forward in time. For this, you have to take into account different scenarios. And since I'm not an economist, I cannot predict what will happen. Actually, economists cannot predict either. But since I cannot predict what will happen in the future in terms of, say, CO2 emissions, I can take scenarios which were considered in, by the IPCC, and then use the same climate model to integrate forward in time. Okay, so we've seen that the sun has a large effect on climate. What does it mean in terms of climate or understanding climate change in the 20th century and 21st century? The standard picture is this. Global circulation models give us very high sensitivity. And this high sensitivity is consistent with the fact that over the 20th century, standard models, or the standard picture of the IPCC tells us that we had mostly anthropogenic forcing, which is responsible for climate change. In order to explain the observed temperature, you need to have a high climate sensitivity in order to do that. Again, you have a given radiative forcing, which is just the human, or primarily the human forcing. In order to explain the observed temperature increase, you need a high climate sensitivity. Okay, this high climate sensitivity is consistent with what global circulations model give us because they have recipes for cloud cover that give us a high sensitivity. This high sensitivity then implies that given emission scenarios will give you a large temperature increase over the 21st century. But we have an additional positive forcing, and that is the sun. The sun has contributed an additional positive forcing, so the total forcing is now larger. It's perhaps twice as large, if not even more. This means that in order to explain the 20th century temperature increase, we now need a low climate sensitivity, and this low climate sensitivity is actually consistent with the data, with the real world. We have seen that CO2 didn't have a large effect over geological timescales, or that climate sensitivity has to be low in order to explain the volcanic eruptions. Okay, so the solar forcing gives us a larger forcing, and in order to explain the temperature increase, we need a low sensitivity, and that is consistent with observations. Okay, so it's a consistent picture. This low climate sensitivity tells us that the temperature increase over the 21st century is going to be low as well. How low? Now we can plug in the models, the model that we have built in order to integrate forward in time, and we integrate parameters which produce 20th century temperature increase, which is consistent with what is observed. We integrate it forward in time, and this is what we get. This is the range of temperature increases that we get with the model. And for comparison, these are the IPCC predictions. Okay, so let me summarize. There are many problems with the IPCC interpretation of the data. And in particular, what you can say is that you cannot support the claims that were claimed, such in particular the fact that CO2 is the primary climate driver, because there's no proof for it. And in fact, if you check carefully, you find things which are inconsistent with the fact that CO2 is the primary driver. In particular, you necessarily need a high climate sensitivity, which is inconsistent with observations. We've also seen that there is a large amount of evidence supporting the fact that the sun has a large effect on climate. And the model or the physical theory mechanism that can explain that the best is the fact that cosmic rays affect the climate. How large is this link? It's about 1 watt per square meter change in the radiative forcing over the solar cycle and over the 20th century. It means that part of the temperature increase over the 20th century, something of order half, is because of the sun. But more importantly, it means that the climate sensitivity is on the low side, and the temperature increase over the 21st century is going to be about 1 degree if we double the amount of CO2. But I'm doubtful we'll be able to increase the CO2 by a factor of 2, because long before that, we won't be burning fossil fuels. Someone once told me, you know, the Stone Age didn't end because we ran out of stone. Okay, let me end with a quote, quoting Al Gore, quoting Mark Twain. He said, what gets us into trouble is not what we don't know, it's what we know for sure that just isn't so. Okay? I think you understand why he said it and why I'm saying it now. Okay, and with this, I'll end.